looking for that. Yeah, okay. So the technological developments that are taking place, as we talked about, it also requires that we think ahead of time, and we need to think what the changes will be, because we have seen many businesses which are now not in existence because they are not able to catch up with time. So we need to also think with regards to what's going to happen down the line, 10 years, 20 years, 100 years. Then that gives a greater feel and for a man to develop himself. So we need to think of concrete in the days to come. Rather, I would say we are in the 21st century. What may happen to this particular concrete in the next century that things to be introduced 100 years from now. Hello.
So there was slight interruption in the connection.
Yeah, that's what. There is some problem with the connectivity.
Okay.
Is it okay, sir?
It's okay now.
Yeah.
It's okay.
So what we need to use 100 years later may always be available around us, but our awareness to understand these concepts and materials and then incorporate suitably is an important aspect. If you look at concrete for the last 100 plus years, there has not been a much change. That means there has not been a material which can completely replace reinforced cement concrete, as all of us agree upon this. So, but reinforcement, that is the steel. If you look at these metropolitan cities, the skyscrapers, the new materials have made all these things quite possible. The advantages of FRP, just to know in general, the main thing is the high strength to weight ratio. They are light.
Excuse me, sir. Sorry to interrupt. Injaganeri, sir.
Hello, Injaganeri, you are muted.
I don't know what's happening because all were muted. Even I am also muted, I suppose. Are you able to hear, sir, now?
Now you are audible.
Okay. There is some problem. What's happening? I don't know what's that.
Sir, again, I think you can just switch off your video so that the connection will be much more better.
Okay. I'll just check that. Is it okay, sir, now?
Now it's okay. You are audible now.
Okay. So non-magnetic and non-conductive in nature, these FRP materials, design can be tailor-made with material properties, fatigue resistance, high
Excuse me,
reliability.
sir.
Yeah.
Sir, your screen is not visible now.
The
Can you just...
PowerPoint screen is not visible.
Is it visible, sir, now?
Yeah, it's okay, sir. Now.
Yeah, it's okay.
Then high fatigue resistance, high reliability, then good finished products, low tooling cost, then impervious to pests and woodpecker attack, environmentally safe, no leaching of toxic chemicals into soil, less maintenance, and life cycle cost. Then what is FRP? We have basically fibers which have been reinforced the constituents retain their identities. Hello, sir.
Sir.
You're audible now.
Okay. Yeah. The constituents retain their identities, that is, they do not dissolve or merge into each other, although they act in concert. Normally, the components can be physically identified and exhibit an interface between each other. So the concept is very much similar to reinforcement concrete, where steel is being reinforced in the concrete. Here, the fibers are being reinforced in the polymer or the resins, what we call. So plastics, these are durable but have low strength. The fibers, if you take glass fiber, it has high strength but brittle. Fiber reinforced polymer, it is going to be having a combination of these two characteristics of the materials, that is durable and the high strength. Compared to other engineering materials, composites have different properties. The difference between composites and other materials. What we assume in reinforced cement concrete, that the material is homogeneous and isotropic, but on the contrast, the fiber reinforced polymer composites are inhomogeneous and anisotropic. That means they do not have the properties, the same properties in all the directions. If you look at the history, composite materials are not new. They have been used since many centuries, rather I would say. The concept is not new. They have been used since antiquity. Straw in clay, brick, the other small products that you quite commonly see are the boat hulls, the pressure vessels, submarine parts, rocket shells, aircraft components, automobile bodies. You look at any commodity now, they are all made out of FRPs. Windmills, chimneys, mine sweeping vessels, swimming pools, partitions, doors, furnitures, in all walks of life, these have become very common now. Domestic applications, plenty, bathtubs, covers, railings, housing components, architectural components, ladders, electrical equipment, pipes, gears, then recreational users, fishing rods, tennis rackets, then sky equipments, then golf clubs, then recreation boats, skates, etc. The other terminology of the classification, these are multi-phase material with significant proportions of each phase. Matrix, it's a continuous phase. Purpose is to transfer the stress to other phases and protect phases from environment. We have in this varieties, whether it is metal matrix composites, whether it is ceramic matrix composite, or it is polymer matrix composite. So they are all in dispersed phase. The purpose here, the fibers enhance matrix. This MMC, they increase the yield strength, the creep resistance. The CMC ceramic, they increase the temperature resistance. PMCs, they increase the modulus of elasticity, the yield strength, and the creep resistance. Now, if you look at the fiber reinforced polymer composites, the whole terminology will always confuse the researchers. FRP, popularly known as fiber reinforced polymer, apart from that, we also now have in the present day the basalt fibers that are being used, that have got a significance in the field of civil engineering applications. Then classification of these composites, if you look at in a broader sense, composites can be classified as particle reinforced, fiber reinforced, then from the structural aspect, either laminates or sandwich panels. These fiber reinforced, the fibers can be in the form of continuous fibers or they can be discontinuous in the short lengths. In the construction industries, also it is widely being used. Roads, highways and bridges, ports, harbors and waterways, electric power generation and telecommunication, water and wastewater transmission, rail and mass transit, retrofitting, and the benefits of in construction are design flexibility, compound surface shapes, oriented strength. The main advantage is that in the direction of the fiber orientation, you can get the desired strength, high strength to weight ratio, corrosion resistance, tailored surface finish, dimensional stability, low thermal conductivity. So the constituents, if you look at in FRP, the main constituents being the fibers and the matrices. Matrices in the sense it is resins or the polymers. Apart from that, we also use coupling agents or the fiber surface coating. So this is an agent is compound which provides a chemical bond between two dissimilar materials, usually an inorganic and an organic. And fillers are also being used. Fillers not only reduce the cost of composites, but also frequently impart performance improvements. For example, these fibers plus matrix plus coupling agent and the other fillers and additives depending upon the requirement may be used to form thin ply, what is known as a lamina. So when you have a thin ply, the orientation of the fibers may be unidirectional continuous fibers, they may be bidirectional continuous fibers, they may be multi-directional continuous fibers or unidirectional discontinuous fibers, and random also discontinuous fibers. The laminate, it is the stacking of various laminas, individual laminas consolidated and to formulate the appropriate thickness to give the requisite properties or the strength. The properties of fiber reinforced polymer composites, they vary depending upon the type of fiber and the resin that is being selected, then the fiber content, the volume fraction of this fiber content, the fiber orientation, as well as the manufacturing process. In new constructions, we have unlimited applications. It can be used as per our choice. The structural components also can be cast, that is beams, columns, bridge decks, then reinforced concrete, we have internal reinforcement. Then apart from that, pre-stressing and post-tensioning, then external reinforcement. In the similar way, these things also can be used. So some of the products that you can see, the structural shapes that are being manufactured through the pultrusion process, they can be in various shapes as our steel structures. They look as elegant as that or even more elegant than that. Then the repair for beams, columns, and walls for retrofitting. The temperature applications in the range of 300 to 500 degrees centigrade. The main difference between the thermoset and thermoplastics. The primary difference is that the thermoset is a material that strengthens when heated, but cannot be remolded or reused or reheated after the initial forming or initial setting. Thermoplastics, these can be reheated and remolded and cooled as necessary without causing any chemical changes. So they can be reused. As a result of these physical and chemical properties, thermoplastic materials have low melting points, while thermoset products can withstand high temperature without loss of its structural integrity. The other differences that we can have a comparison between these two. So thermoplastic can be synthesized by the process called addition polymerization. Thermosetting plastics are synthesized by condensation polymerization. Thermoplastic is prepared by injection molding, then extrusion process, blow molding, thermoforming process, and rotational molding. They are the different processes. Then thermosetting plastic is processed by compression molding, then reaction injection molding while at the time of manufacturing. Thermoplastics have secondary bonds between the molecular chains, whereas the thermosetting plastics have primary bonds between the molecular chains and hold together by strong links. Thermoplastics have low melting points and low tensile strength, whereas the thermosetting plastics have high melting points and tensile strength. Thermoplastic is lower in molecular weight compared to thermosetting plastic, and thermosetting plastic is has a high molecular weight. Some of the commonly used materials as thermoplastics and thermosetting polymers are thermoplastics. We have polystyrene, Teflon, acrylic, nylon. Then thermosetting, vulcanized rubber, then bakelite, then polyurethane, epoxy resin, vinyl ester resin, etc. They are only indicative in nature, but there are many that can be used. So in summary, if you see, wide varieties are available in terms of resins. Selection is based on physical and mechanical properties of the product, then fabrication process requirements. Fiber, cellulose, sisal, and all these have been used widely since many centuries or many decades. Natural fibers, all these fibers are grown worldwide and are commonly available. They are used for making ropes, carpets, bags, etc. Recently, natural fiber reinforced polymers have created interest in the automotive industries for varied reasons. Environmental friendly, they are biodegradable. Energy required to produce them is very small. The density of fibers is in the range of 1,250 to 1,500 kg per cubic meter compared to our reinforced cement concrete, which is around 2,500 kg per cubic meter. And whereas for e-glass, which is used as a reinforcement, that is around 1,800 to 2,100 kg per cubic meter. That is 1,800 or 2,540 for e-glass and 1,800 to 2,100 for the carbon fibers. And including the reinforced cement concrete, it is around 2,500. The advantages of the natural fibers are the modulus to weight ratio of some of the natural fibers is greater than that of the e-glass fibers. That is, they are competitive with e-glass fibers in stiffness critical design. Whereas the natural fibers provide higher acoustic damping than e-glass and carbon fiber composites. And carbon fiber composites, they are suitable for noise attenuation, which is important in requirement in interior automotive applications. Then natural fibers are less expensive than the glass and the carbon fibers. The limitations of the natural fibers or the disadvantages being the tensile strength of the natural fibers is relatively low. I would rather say it is not very low. Low melting point and moisture absorption, and at temperatures higher than 200 degrees, they start to degrade. Coming to some of the man-made fibers which are commonly used: aramid fibers, boron fibers, carbon fibers, then glass fibers, basalt fibers, then even nylon, polyesters, then polyethylenes are also being used. Polypropylene, they are also being used. So these are the continuous ones, what are known as the rovings. They all come in the circular bundles. Then these are called as the woven rovings, which are woven in the single direction or in both the directions. Then chopped strand mat, how they look like, some of the examples. Then the other common forms being these rods, strips or plates, then the fabrics. Cables, gratings. Then these fibers within the matrix, they can be arranged in the plies in different directions. One is parallel to the application of the load, 0 degrees, 45 degrees, minus 45 degrees. Price. They are just a comparison between the three which are commonly used. The selection is going to be based on the required strength and stiffness, the durability consideration, and obviously the cost constraints and the availability of the materials. Coming to these glass fibers, they also been classified into different types. These are the most commonly used in structural applications. They are available in several grades. One is called as the e-glass, normally considered for electrical insulation, well suited to applications in which radio signal transparency is desired, such as aircraft, radomes, antenna, and printed circuit boards. Then alkali resistance, it is normally terminated as AR glass. Then another one, S glass. This is 40 to 70% stronger than E glass, and this is used for military applications, missile casings, and aircraft components. Then they have high strength, 3 to 4 gigapascals, moderate modulus around 50 gigapascals, then medium density. Used in non-weight modulus critical applications. Carbon fibers, which they typically look like, as it is quite common to us, significantly higher cost than the glass, then high strength and high modulus with low density. E varies approximately between modulus of elastic 250 to 300 GPa for standard, for intermediate 300 to 350, and 350 to 550 high, and even ultra high to the order of 550 to 1000 gigapascals. Superior durability and fatigue characteristics used in weight modulus critical applications. Aramid fibers, moderate to high cost. Two grades are available normally, 60 GPa and 120 GPa elastic moduli. High tensile strength, moderate modulus, low density, low compressive and shear strength. And some of the durability concerns are the potential UV degradation of these fibers, then potential moisture absorption and swelling that's possible. There are several manufacturing processes which are commonly used. The most simplest amongst all is the hand layup or the spray up. Then the second one, resin transfer molding, popularly known as RTM, then compression molding, then injection molding, reinforced reaction injection molding, RRIM, pultrusion process, which is very common, wherein the reinforcing bars can be manufactured using this technique and quite commonly used in all structures now. Then filament winding, then vacuum assisted RTM, then centrifugal casting. Products made for utility structures are widely manufactured in several ways, but the commonly used ones are the pultrusion and the filament winding. The typical schematic representation of a pultrusion process, you have a reinforcement which is in the form of rowings that is being kept there. Then it is impregnated into a resin. Then it is subsequently being cooled. Then you have a downstream tooling and you have an upstream tooling, wherein at the end, based on the desired length what is required, these are being automatically cut off. So this is a very simple way of getting the required members for structural use. This is another schematic representation, manufacturing process for the filament winding. You have the resin and you have a mandrel over which this is going to be impregnated and it is going to be wound around. So here, utility poles, columns, bridge girders, pipe, missiles, aircraft, it can be used for many. This is another schematic representation of the same manufacturing process. This is a typical old photograph of the filament winding machine, how it looks like. The fiber properties, if you look at steel and make a comparison with regards to the different fibers that are commonly used in civil engineering applications, and the typical stress strain representation of these particular materials when tested in the laboratory, steel has tested in the laboratory, the typical CFRP stress strain diagram is linear. Right from the loading point up to the failure. The steel bar, what we have, it will have enough ductility, or it has got at least what is the required ductility, especially for the mild steel. And the pre-stressing steel also, if you look at and make a comparison between these three, at failure, the failure strain for CFRP is very low as compared to our steel bar. That's one of the major drawbacks of this particular material when it is being used in applications, civil engineering applications. The failures are going to be very catastrophic. The other properties, if you compare with regards to these several commonly used fibers, yield strength typically for steel, I would rather say it varies between around 270 plus to 500 plus. Then whereas the tensile strength is around 480 plus to 690, and elastic modulus is around 200 GPa, then the rupture strain is of the order of 6 to 12%. Whereas that for GFRP, it is 483 to 1600 the tensile strength, 35 to 50 the elastic modulus being low as compared to steel, and the rupture strain is to the order of 1.2 to 3.1. Then CFRP on a similar basis, the tensile strength is of the order of almost 600 to 3690. Elastic modulus is of the order of 120 to 580. Then rupture strain is to the order of 0.5 to 1.7. It has very high tensile strength, but its rupture strain is very low. That's one of the drawbacks of carbon reinforced polymer composites. The aramid fibers, they also have a good tensile strength. It is in the order of 1720 to 2540, and the elastic modulus is 41 to 125, and the rupture strain is 1.9 to around 4.4. Similarly, for the natural fibers, if you so the composition, typical composition when we look at for the different types of the e-glass, that is classification either E, S, then A and C like that. The use is electric insulation for the e-glass, then high strength composite, they have very high strength, then high strength composites with the stringent quality control, that is named as S2, then thermal insulation, then chemical applications. So the typical combination for e-glass will be around 55% of SiO2, 11% of Al2O3, and 6% of B2O3, 18% of calcium oxide, 5% of MgO, and 5% rest of the other materials. So in a similar way, the compositions vary for these particular things for the same fiber manufactured in different ways. So the other typical properties are also being given, the percentage elongation, the Poisson's ratio, the shear modulus, typically for some of these commonly used fibers. Steel versus composites, if you look in general, steel, low material cost, high installation cost, these are corrosive, these are having more weight or density, then fabrication is required, then high maintenance cost. Similarly, if you look at the composites, they have high material cost, low installation cost, non-corrosive, lightweight, then no fabrication required, and low maintenance cost. So in general, if you look at composites have many advantages over the steel. Some of the applications, if you look at it, the enormous variety of applications in which FRPs can be effectively used in structural engineering and infrastructure applications, as we talked about, because of different types of shapes and properties of FRP materials. The use of FRP it will depend upon whether the applied load is tensile or compressive, and to highlight, it has a better tensile strength as compared to a poor compressive strength. The response of an FRP material in tension is dependent largely on the failure strains of the two component materials. So it depends upon the resin as well as the fiber, as it happens in the case of reinforced cement concrete. So these are some of the typical photographs of carbon and glass fiber, and as already we have discussed about the stress strain for the different types of fibers, that is e-glass, aramid, standard carbon, then reinforcing steel. So reinforcing steel is the one which is there horizontal. The strength and stiffness of FRP are governed by the fibers. However, the overall behavior depends upon the mechanical properties of the matrix. The other important thing is the fiber volume fractions, what we call, that is the volume of fibers per unit volume of FRP. Then the fiber cross-sectional area that is available, that is the percentage of reinforcement, what we talk about. Then orientation of the fibers within the matrix and the method of manufacturing. And it is the interaction between the fibers and the matrix that gives FRPs their unique physical and mechanical characteristics. The orientation of the fibers within the matrix is a key consideration in the design of the use of FRP materials. So the response of an FRP material in tension is dependent largely on the failure strains of the two component materials. So the one is the matrix, the another one is the fiber. So in between these two, we'll be able to get the corresponding properties of the fiber reinforced polymer composites. If the failure strain of the matrix is less than the failure strain of the fibers relatively, and the fiber volume fraction, what we normally designate it as VF in the design, is small, say approximately less than 0.1, then the failure of the FRP is governed by the matrix itself. However, if the fiber volume fraction is large, that means the quantity of fiber content is more, then the fibers carry the majority of the load. Then the failure of the matrix is not critical. Then the failure, that is the load carrying capacity, will be much more until and for carbon FRPs respectively. So in that particular case, relatively for the aramid, the compressive strength being very low, and that for carbon it is being very high. Aramid fibers perform particularly poor in compression, and as a consequence, FRP strength is commonly neglected when acting in compression when used as an reinforcement in concrete. So in the case of protruded FRP structural sections in compression or bending, the compressive strength of FRPs is relied upon to carry the load. So the fatigue resistance of these FRP materials, especially the carbon FRPs in particular, they have very superior fatigue characteristics compared to the other fibers. Then some of the structures Michigan, which is constructed in 2001, completely pre-stressed and reinforced with CFRP, 3 simple spans, T-beams pre-tensioned with CFRP tendons and post-tensioned also. Then this is one of the street bridges in Michigan in USA. Extended lifespan estimate is around 100 years. Then predicted significant decrease in maintenance cost. Then 5-year load test produced favorable results. So these are some of the other typical applications, the reinforcement that is being shown. These are the bridge decks. Culverts. The other applications you can see in automobile, you can see in recreation, you can see in aircraft, that is aerospace engineering, then wind energy and many applications. So these are some of the typical photographs of these FRP applications. These are some of the protruded structural frames. Even aesthetically, they can be made very beautiful to the shape that is desired. So this is GFRP composite, a classroom system which is being constructed 1974. And some of its applications in retrofitting, very efficient, and it regains its original strengths. So some of the typical photographs. So this is the retrofitting of the piers of the bridges, girder strengthening, column wrapping, then pier upgrades, then deck stiffening. So all things are possible using these FRPs. So highly corroded, which can be strengthened. GFRP wrapping for the piers. CFRP wrapping for the. So this is one of the Bible Christian bridge where the strengthening is being taken up, retrofitting is being done. Then strengthening of the pier caps and experimental study. So architectural fiberglass sculpture at Athens. So some of the unique structures of GFRP. Then the innovative shipbuilding design, stadiums. So one of the small things which I would like to talk about is with regards to one of the GFRP composite bridge deck, which has been cast by hand layup and being tested by one of the research scholars, namely Veer Sudarshan Reddy, which Professor Babu Kurian also may be knowing about the person. So the first aspect was to make the wooden molds, each cell cross section of the deck, then contact molding hand layup process, fabrication of individual cells, that is the middle and the end cells, assembling these particular cells, then wrapping schemes, then finishing work, then the final product. These were the processes that were involved. So the materials that were used were resin vinyl ester, reinforcement ECR glass, oven rowing mat of 600 GSM, then accelerator, cobalt naphthenate, then promoter dimethylamine, then catalyst methyl. The first coat of the resin on these, then glass fiber oven rowing mat of 600 GSM is being used and wrapped around this wrapping scheme on the end cell after the resin was being laid, and subsequently again they will put the resin after each layer of it. And he is Dr. Sudarshan Reddy, our batchmate and a research scholar at IIT Madras. Then the application of these rollers in order to see that there is enough bonding between the resin and the fibers, and that the air gaps are being removed. So this is one of the triangular cells. Then assembled component decks. These two are the end ones and this is the middle one before it is being finished. So this is another layer of mat that is being wrapped and the things are being assembled in position. So here they had a mechanism to rotate so that it can be easily wrapped on all the faces. So this is the overall view of the fabrication setup, lifting of deck and shifting it. So trimming of the deck was also being done very precisely. So this is the cross section of the fabricated panel. Length was approximately around 3 meters, width around 1 meter, and depth around 30 centimeters. So this is another longitudinal view of the deck. So the experimental study, it was static testing, different positions of patch load was applied, and IRC class A wheeled vehicle up to failure. fatigue testing around 10 kilonewton to 83 kilonewton and 83 kilonewton to 400 kilonewton for frequency of at a frequency of 1 hertz around 200 million cycles. Then static testing of fatigue tested GFRP composite bridge deck panels up to failure under monotonic loading. Then they were also tested for shear capacity. So this is a typical test setup in the structural engineering lab, IIT Madras, where myself and Professor Babu Kurian happen to also do our PhD. So this is a schematic representation of the testing. These are the locations of the strain gauges in the cross section. In the supports for testing, how they were, and simulation of the wheel load and the dead load on the bridge deck panel. It was done using the slotted weights, and neoprene rubber pad also is being used for that. So this is the pumping unit. This is the top view of the testing. And after the testing, the rupture of the fabric took place at these particular junctions. So these were some of the coupons which were being tested for the material properties, wherein the strain gauges used for the load, that is Charpy and Izot. So this is with regards to the top surface after the testing. This is for a typical shear test. In some of the locations, there was also a delamination what was being observed, the type of failure. So in that cell, I would rather say FRP as a material in civil engineering has got very high strength, high resistance to corrosion and chemicals, high resistance to elevated temperature, high resistance to abrasion, then high toughness, fatigue resistance, lightweight. The advantages being weight saving leads to fuel saving, increase in payload or increase in range which improves the performance. Then good fatigue resistance leads to enhanced life, which involves to saving in the long-term cost of the product. Then good corrosion resistance means fewer requirements for inspection, which results in the saving of the maintenance cost. Ease in fabrication, manufacturing, handling, erection, then year-round construction possible, high performance, then high durability, excellent strength to weight ratio. So disadvantages, some of the disadvantages: high initial cost, susceptible for creep and sinkage, global and local buckling possible, aerodynamic instability with lightweight, then requires highly trained specialist for the construction. Then lack of standards is one of the major problems, and the design guidelines one of the problems while using. This was earlier, but now sufficient guidelines are also have come up, and with these people are able to manufacture this particular product. Within the time that is being allocated, I was just able to superficially give you the application of these FRPs in civil engineering. I think if there are any questions, to the best of my knowledge, because I do not work in this particular field, it was only the knowledge that I had gained at the time of doing one of the courses at IIT Madras. Babuji?
Yes, sir. Yes, sir.
Yeah, yeah. If there are any questions or if there is anything, I would be happy to.
The participants are requested to ask questions.
I hope there is no disturbance in the audio, Babuji.
No, I don't have any audio. No, now there is no problem.
Okay, okay. Initially there was some disturbance.
Yeah, initially there was some disturbance was there.
Okay, okay. How many branches now in the college? I don't 5 or 6.
Pardon?
How many branches or disciplines of engineering in
Yeah,
your
now 6, sir.
6?
6
Civil, computer science, electrical.
computer science, AI, and computer science. Then
Okay,
civil, mechanical, electrical, and electronics.
okay. And postgraduate studies?
Postgraduate studies are 2.
Okay, okay, okay. Which are the in civil engineering also you have one?
No, civil
postgrad-
engineering we do not have. At present, we are not started. Then for computer science and electronics, one branch is there.
Okay. So who's this one is there session now after this?
Yeah, today there are 3 sessions. This is the
Another
first
2?
one. After this,
Okay.
2 more are there. In every day, 3 sessions are there.
Okay, okay. Again, Pradeep and others are also there. Revati?
Yes, sir, I am there.
Pradeep is there.
There. Sitting here. Very nice. Okay. How are you, Pradeep?
Yeah. I am a little bit better than that day I spoke to you.
Okay, okay, okay.
I'll call you later, sir, sometime.
Yeah, no problem. Yeah.
So it's nice. You are very good talk, sir.
Thank you.
Babu, sir.
Babu, sir.
Yeah, Pradeep.
Can I see your face once?
Pardon?
Your video is not on.
Yeah, video. Okay. Yeah, now it's okay.
Yeah. Now it's okay.
Okay.
Actually, I had a class. I missed the initial portion of.
Initial portions.
Yeah.
Okay. Yeah, he actually inaugurated the program.
Yeah. That time I
The
missed.
speech was very good.
Yeah.
And his presentation also was very good.
Very good.
The only problem is that in between some disturbance was there.
Oh.
That's the only thing. Otherwise, it was good.
Okay, sir. Okay. So my topic you have changed, right?
Yeah, it is changed. After that, I did not circulate, but it is changed.
Okay, then. Okay, that's fine.
It's that. The Robin's topic
Robin
is
also is there.
Yeah,
Pardon?
Robin also there, and without knowing, almost close to.
Yeah, Robin's topic is now on Thursday afternoon because Rajiv want to do the presentation tomorrow.
Okay.
He is
Okay,
having
so-
some programs the day after tomorrow. So I asked Robin, he agreed to do it.
Okay. So tomorrow, first Revati, then Rajiv, then me.
Revati, Rajiv, and yourself.
Okay, sir. Okay.
Okay, sir, then.
Okay, sir.
If there is no other this
I am
one, we'll
requesting
take
the
it.
participants, please,
Uh,
please ask them some questions if you are having.
Okay,
Regarding
sir.
FRP. Yeah.
Sir, can you hear me?
Yeah, please.
Sir, I am Sara from 5th semester.
Okay.
Sir, I just wanted to know that can we fully replace traditional steel with FRP?
Yeah, it's already replaced. There are many structures which are being constructed presently within India and even abroad also. And there are a lot of research also going on in the premier institutions of IITs and NITs also. So all these pertrusion process, it is possible. Earlier, it was not possible to use this reinforcement for shear. It was very difficult to have this bending of these particular bars. And these are more applicable in the marine environment where corrosion is one of the major problems.
Sir, is it fully effective in taking shear?
Yeah, it's effective. The earlier problem was that there was a poor bond between this material and the concrete when they are being used as FRP bars in the concrete. Now the corrugations are also being made as on the in the case of the steel reinforcement, and there is now enough bond strength also between these FRP bars and the concrete. So as a flexure reinforcement, as a shear reinforcement, they are very widely used now.
Okay, sir. Thank you.
Yeah.
Any more questions, please?
Yeah, if there are no more questions,
Okay, sir.
yeah, we'll take leave.
Participants,
minute.
is there any
1
more
minute.
questions from your side? Okay. So I would like to thank you, sir, for such an informative session on application of fiber reinforced concrete in civil engineering. In spite of some audibility issues in between, I'm sure the participants have got an insight into such a relevant topic in civil engineering. So please accept our sincere appreciation for the insightful presentation on fiber reinforced concrete and thanking you for sparing your valuable time and knowledge with us. Also, we look forward to your informative sessions in our future events as well. Thank you, sir.
Oh, thank you, man.
Dear
I'll take leave of you,
participants,
Babuji.
Yeah, thank you,
Okay.
Injaganeri.
Yeah, we'll talk
Okay,
later. Thank
I
you
will
very
call
much.
him.
Yeah.
I will call him. Okay, bye.
Bye.
dear participants, our next session on behavior of autoclaved aerated concrete masonry blocks by Dr. Bijli Balakrishnan will start from 11:45 a.m. I request all of you to join